Adelaide is a city in South Australia and it's one heck of a complicated place geologically speaking. The rocks here are ancient and have undergone several tectonic events that have led to a complex and somewhat confusing array of geological features in present day. Beneath the sediments of the Murray Basin is a truly ancient volcanic arc that roared to life at some point 800 million years ago. This volcanic arc was formed by subduction processes and it released violent explosive eruptions with pyroclastic flows that covered the then barren land beneath vast amounts of volcanic material. But along with this, the area also experienced another tectonic event. A rift zone formed to the west of the arc 830 million years ago, and the two may have occurred simultaneously. This rift is known as the Adelaide Fault Belt, and it's a geosyncline. A geosyncline is a large-scale depression in the Earth's crust that's filled with thick sequences of sedimentary and volcanic rocks. This geosyncline rifted at least 5 times in its history, and the reason it formed is thought to be associated with the breakup of the supercontinent known as Rodinia. This rift basin was later to form during the Delamerian orogeny approximately 514 to 500 million years ago, when the region experienced significant tectonic compression due to a subduction event in Western Victoria, which led to the folding, faulting and metamorphism of the sedimentary and volcanic rocks in the geosyncline. This orogeny uplifted the region from a flat basin to towering mountain peaks, and it transformed the region into a complex fault belt, as well as depositing vast mineral wealth in the process. If you live in Adelaide, you are literally a short drive to the goldfields. But this video is about the largely hidden Nackara volcanic arc. This arc is now being investigated with the suspicion that it holds vast untapped mineral wealth in the form of copper and gold porphyritic deposits, along with a host of other metals and rare earth elements. Porphyry intrusions occur primarily at the end stages of volcanism as the magmatic system begins to die down. Small-scale mining was conducted in very specific areas around this arc in the early days of the gold rush, but it wasn't known to be a volcanic arc back then. It's only when we view the region under magnetics that we can get an idea of just how vast this arc stretches, and boy is it a big one. When this arc roared to life, the erosion of it filled the Adelaide geosyncline with volcanic deposits along with sedimentary deposits that dominate it. Outcrops of this arc are rare to say the least. But there are very specific places where diapirs related to this volcanic system were deposited. We'll look at them soon. The porphyry intrusions of the Nackara volcanic arc are thought to host gold and copper in economical amounts, meaning it could be rich enough to mine on a large scale, and exploration and drilling are still underway to deduce the richest areas of the arc. Due to its age, the exact identity of the oceanic plate involved in the subduction process leading to the formation of the Nackara volcanic arc is not precisely known, but can be referred to as the Proto-Pacific Oceanic Plate, which subducted from the west to the east beneath the stable continental craton known as the Gawler Craton, which is truly ancient in its age, with its formation dating all the way back to 4 billion years ago. As a side note, if you're enjoying this video, please click the like button to help YouTube recommend it to others. We also have a Patreon if you'd like to support the channel, only if you have the means of course, and you can find that both in the description and in the pinned comment down below. If you've watched the previous video that I've made on the Stavely volcanic arc, linked down below, you'd know that its birth was during the Cambrian 520 million years ago. This coincides with the birth of the Delamerian orogeny in the Adelaide geosyncline, which squashed, bended and buckled the sediments and volcanic material, forming a vast and towering mountain range in the process. The Stavely volcanic arc owes its existence to the subduction event that took place when the Paleo-Pacific Ocean subducted beneath the Indo-Australian tectonic plate. And as mentioned before, the effects of this subduction event extended beyond Victoria, and it reignited the ancient fault lines within the Adelaide geosyncline, with recent depositions of granites and mafic to intermediate rocks like diorite and gabbro occurring among several other intrusive rock types. It's not only gold and copper that's being explored, deposits of kaolin and rare earth elements are linked to this arc. The tectonic collision that formed the Stavely volcanic arc in Victoria are directly related to causing the Delamerian orogeny. So where can we find evidence of this volcanic arc aside from magnetics? Well, the places where we can get just a hint of this volcanic arc occur in diapirs dating back to the age this arc was active. Volcanic diapirs are a geological phenomenon where magma rises buoyantly through the Earth's crust, often creating dome-like structures as it intrudes into overlying rock layers. And traces of it are scattered within a now highly eroded mountain range that formed during the Delamerian orogeny. When viewed under magnetics, you can see they occur in the northwestern tip of the now deformed, bow-shaped Nackara Volcanic Arc. These intrusive rocks forced their way up into the Adelaide geosyncline and got deposited amongst the many ancient sedimentary rocks that exist in this once rift base and turned mountain range. But the one thing that really stuck out to me was the fact that these diapirs from the Neo-Proterozoic occur far north in places where you wouldn't expect them to be. This is one of those geological mysteries that we are yet to resolve. I must note that I'm now going into speculation territory based on my observations. See these arc-like shapes here? They appear to be sections of the Nackara Volcanic Arc that have been torn away from the main arc. We have the same age diapirs from the Neo-Proterozoic occurring here, and this could be due to the many rifting events that the Adelaide geosyncline underwent. But what's stranger is they occur even further northwest from here too, amongst intrusive magmas like granites that date back to the Cambrian to Ordovician. These intrusives appear like they should be related to the formation of the Stavely Arc and the Delamerian orogeny. Is it possible that the Nackara Volcanic Arc is far larger than previously thought, and that sections of it have been torn away from rifting and the later Delamerian orogeny? Yes, it's possible. You see, the Adelaide geosyncline is also referred to as the Adelaide Superbasin, and it's definitely super in its size. If this entire superbasin rifted, then parts of the Nackara could be far away from the main arc. And I suspect that's what's happened here, as studies have confirmed this rift went up to the region of Lake Eyre, which is exactly where we find more of these Neo-Proterozoic diapirs. Australia is truly an ancient landscape, and many volcanic arcs have formed the vast history of tectonic collisions and mountain building the continent has undergone. We'll continue to explore more of these in future episodes. So until then, thanks for watching. In 1917, the Russian Empire collapsed when the then Tsar Nicholas II was abdicated from his throne. This led to the end of the Romanov dynasty. When this collapse occurred, the price of a relatively unheard of alloy of iridium and osmium, known as osmiridium, soared to record highs. Russia was the land where this metal was primarily mined, and after the collapse, Tasmania would take its place in supplying the world with this precious alloy. This video is about the largely forgotten osmiridium rush of Tasmania, and we'll discuss the geology of how osmiridium became deposited in ultramafic rocks. And we'll also look at some of the weird laws Tasmania has regarding mineral acquisition. By 1920, Tasmania held first place in supplying the world's osmiridium. The high demand for it, which was used in various industries including the manufacture of pen nibs, electronic contacts, and other high durability applications, drove significant export activity. Funnily enough, prior to the boom, osmiridium was seen as an annoying metal for gold miners. In fact, they were charged a price if their gold contained it. This happened because osmiridium was considered an undesirable impurity when gold was being refined. The added cost of refining the gold to remove the osmiridium led to miners being penalised for its presence. Thus, much of it was discarded during alluvial mining, with miners tossing out the alloy in riverbanks whilst mining gold. But this was a very hard task to achieve because osmiridium is actually heavier than gold. So the traditional way of separation through specific gravity and water was impossible to accomplish with this platinum group alloy. And that is why so much of the gold was contaminated with osmiridium in Tasmania. But how did Tasmania become so saturated with osmiridium? Well, the Cambrian 541 to 485.4 million years ago was an intense time for Tasmania. Extremely explosive volcanics roared to life. Earthquakes were tremendous in their scale, and along with this, a rare occurrence of what is known as ultramafic rocks had erupted onto the surface. These ultramafic rocks host the rare platinum group element, and it was being shed from rocks that had become metamorphosed. The main source rocks were dunite and peridotite, and these rocks can be found in the western to middle parts of the Tasmanian landmass, with them outcropping in relatively small areas. In Tasmania, the ultramafic rocks, which were already enriched in platinum group elements, underwent metamorphism during the Devonian period, 419.2 to 358.9 million years ago. This metamorphism likely played a role in mobilizing and concentrating the osmiridium within specific mineral phases, making them more extractable in alluvial deposits. The osmiridium present in Tasmania was primarily hosted in the original ultramafic rocks, and metamorphism helped in redistributing and concentrating these elements in more accessible forms. The osmiridian rush of the 1920s primarily focused on alluvial deposits, meaning miners worked the rivers and tributaries to find the alloy. Placer deposits existed en masse in the streams here, as they had been shed from the host rocks through the process of erosion over tens to hundreds of millions of years. There were two primary rushes that occurred to find this alloy. The first began in 1909 when the price of the metal began to rise. The second occurred in 1925 when the discovery of osmiridium occurred in a region known as Adamsfield. However, by the 1930s the boom had largely passed, and the rush for osmiridium had fizzled out. To my knowledge, the host rocks that contain the osmiridium were never crushed and mined to release the alloy, and the rush largely consisted of alluvial mining of placer deposits. So this is the story of a strange rush for a widely unknown platinum group alloy. Tasmania is different to the rest of Australia. It has very stringent rules regarding prospecting and mining, which I view as unfair. Only companies that had permission to mine the metal were allowed to make a profit from it, as for whatever reason, all minerals in Tasmania belong to the Crown, including gemstones. It's for this reason that Tasmania is still so gold saturated, as there is largely no incentive to mine the metal due to the fact that normal everyday prospectors can't actually sell it legally unless they have very special permissions. If you've ever watched the YouTube channel Tassie Boys Prospecting, you'll witness an abundance of gold being extracted through sniping, which is when a wetsuit is worn and the rivers are manually inspected for gold to be sniped with a sniffer bottle. If you came to Victoria and tried this, it's likely you'll find very little, as unlike Tasmania, miners can legally sell their gold in the state. The same rings true for the rest of Australia. I'm not sure why Tasmania is different, perhaps it's to preserve the ecosystem, but with that being said, these rules were imposed in the late 1800s, during a time when environmental preservation wasn't as widely adopted as it is today. So gold, osmiridium, gemstones and other valuable commodities can't be legally mined to be sold in Tasmania today. I hope you found this topic as interesting as I do, and as always, thanks for watching. Volcanic arcs are the byproduct of subduction zones around the world. They host violent explosive volcanic eruptions, but along with this they also deposit vast mineral wealth into the fractured bedrock, with many volcanic arcs containing significant quantities of gold, copper, silver, lead and other metals. The reason volcanic arcs form is due to the subducting plate. When an oceanic plate collides and descends beneath a continental plate, water is introduced into the mantle in two ways: by the subducting slab dragging oceanic water down with it, and by the release of water from water-saturated rocks when they reach a specific depth, where the heat and pressure force them to undergo metamorphosis. When water is introduced into the mantle, it lowers the melting point and induces partial melt as a result. Minerals become sequestered and concentrated. They are sweated out, so to speak, from the subducting slab, and the magma and fluids that are released begin to travel upwards due to buoyancy, utilising the faults and fractures that subduction inevitably creates to ascend where they can become deposited into the bedrock. This is one of the few ways that volcanic arcs deposit minerals into the land. In northern Queensland, an ancient volcanic arc that formed 298 million years ago during the early Permian exists in the northern part of the Bowen Basin. These volcanics were formed during a subduction event, and they outcrop in various areas. We have a high degree of mineralization in some of these areas with copper, silver and gold occurrences. Other areas, however, are completely devoid of mineralization. On geological maps, the Lizzie Creek volcanic group is represented by a light blue colour. Its formation began when the oceanic Paleo-Pacific tectonic plate subducted beneath the continental Indo-Australian plate, giving birth to volcanoes and major earthquakes. These volcanoes were tremendously explosive in their magnitude, with the release of rhyolite and rhyodacite being pronounced. And we have the later formation of a back arc basin in an area where the land was stretched. This is known as the Bowen Basin in present day. This basin deformed a Lizzie Creek volcanic arc in certain areas, and we have other intermingling volcanics that joined the Lizzie Creek in erupting during the early Permian, and it overlaid it in certain parts, such as the Mount Toussaint volcanics and the Strathbogie trachyte. We also have a group called the Mount Wickham rhyolite on the westernmost border of the arc. where the aforementioned later deformation occurred. It appears as though the stretching of the land occurred in a later part of the Permian, after this volcanic arc had existed for over 40 million years, spewing out explosive and effusive eruptions. What's really cool is under magnetics we can see massive dikes or veins that were emplaced by hydrothermal waters and by magmatic processes. Look at the linear lines that exist so abundantly throughout the region on magnetics. It's possible that these dikes or veins might contain high mineralization in areas and yield an abundance of gold, silver, copper, and other commodities. The red lines that you see on the geological map represent them, and they are numerous and quite widespread in places. Right alongside the Lizzie Creek volcanic arc are numerous major intrusive rocks like the Thunderbird granite. This would have been the fuel source for the volcanoes in the Lizzie Creek complex, and they have been uplifted to the surface. In present day, the mineralization that occurred in the Lizzie Creek volcanic arc occurs most abundantly in the Mount Carlton area. It's only now that we're really beginning to drill into the earth to see if any significant copper or gold deposits exist. Significant is the key word here. There are former prospects that uncovered gold, silver and copper in the region, but they have been small scale and the yields haven't been great enough for small scale miners. This is typical of volcanically emplaced gold, which, as opposed to orogenic gold, doesn't contain the high yields one might expect or hope to see. But volcanic gold is normally concentrated in certain areas, due to a process known as magmatic differentiation. Magmatic differentiation occurs as magma rises through the Earth's crust. As it does, different minerals crystallize out of the magma at different temperatures. The result is a concentration of valuable minerals like gold, copper and silver in certain places. This can lead to extremely high yields if the right place is drilled that contains a deposit that was emplaced by magmatic differentiation. The result is a bounty of gold or other metals. Open pit mines are often used to extract these minerals. The Lizzie Creek volcanic arc is one of many examples of these kinds of volcanic remnants. Ancient volcanic arcs are scattered all over Australia, speaking to the many different tectonic events the country has undergone throughout time. So this is the story of a once mighty volcanic arc that eventually died off and left behind the remnants and riches from the time when it roared to life, to the point where the magma finally cooled. Thanks for watching. Western Australia is one of the oldest lands in the world. It's also one of the most mineral-enriched places in Australia, with valuable deposits of many different commodities including banded iron formations, gold and other precious metals and gems. It's famous for having large gold nuggets at surface level, and many people make a living detecting for gold in the goldfields in the eastern part of the landmass. The goldfields are located within the Yilgarn Craton's Greenstone belts, composed of ancient volcanic and sedimentary rocks. A greenstone belt is a geologically significant zone composed of ancient volcanic and sedimentary rocks that have undergone metamorphism. These belts are typically found in the Archean and Proterozoic terrains and are some of the oldest parts of the Earth's crust. They are named greenstone because of the greenish hue imparted by minerals, which form during the metamorphic processes. Greenstone belts are globally significant for their rich mineral deposits, particularly gold. During tectonic activity, the greenstone belts often undergo significant deformation, which creates fractures and faults. These structures serve as conduits for hydrothermal fluids, which are hot mineral-rich waters that move through the Earth's crust. The metamorphic processes within greenstone belts often lead to the concentration of gold in certain minerals. The Kalgoorlie goldfields are an excellent example of gold deposition in a greenstone belt. What's amazing is that the Kalgoorlie goldfields were once part of an ancient mountain range. This mountain range was formed during the Archean Eon, approximately 2.6 to 2.8 billion years ago, through a series of geological processes that included tectonic activity, volcanic eruptions, and a collision and accretion of various crustal blocks. This ancient mountain range has been highly eroded, and through the process of erosion over billions of years, gold was deposited en masse all around the area. This helped to concentrate gold in alluvial deposits, which were easier for early prospectors to discover and mine. The Yilgarn Craton, which includes the Kalgoorlie region, experienced significant tectonic activity during the Archean Eon. The tectonic processes, including subduction, collision, and accretion of various terrains, led to orogeny, which is the process of mountain building. These processes created significant uplift and deformation, forming an ancient mountain range in what is now the Eastern Goldfields region of Western Australia. The rocks in the Kalgoorlie region were subjected to intense heat and pressure during these tectonic events, leading to metamorphism and deformation. This metamorphic activity contributed to the development of extensive fault and shear zones, which later played a crucial role in gold mineralization. If we look at the geological maps, we can see that the entire area is primarily composed of very ancient volcanics. From mafic to felsic eruptions, the volcanoes that released these layers of rock were both highly explosive and effusive at times, and sometimes they were intrusive, meaning the magma cooled in the earth before erupting. And these have also been exposed to the surface through the marked erosion that has occurred here. We also have occurrences of ultramafic rocks. Ultramafic rocks are relatively rare compared to other rock types due to their deep mantle origin and the specific tectonic processes required to bring them to the surface. They are igneous rocks with very high magnesium and iron content and very low silica content. They are the primary constituents of the Earth's mantle. However, because the mantle is deep beneath the Earth's crust, these rocks are not commonly found at the surface. If we expose the fault lines here, we can see just how fractured the Earth is here. These fault lines served as valuable pathways for gold-laden metamorphic fluids to travel through and become emplaced when pressures dropped as it rose to a certain depth within the Earth when the fluids solidified into gold-bearing quartz. On magnetics, we can see the clear indication of ancient greenstone belts. Parts of the greenstone belts in the Yilgarn craton likely originated in volcanic arc settings, where oceanic crust was subducted beneath continental or other oceanic crust, generating volcanic activity. But the greenstone belts also contain sedimentary rocks like shales and sandstones, which were deposited in basins adjacent to the volcanic arcs. The greenstone belts have experienced multiple tectonic events, including rifting, which is the splitting apart of the land, and accretion, which is the coming together of crustal blocks. These rocks have undergone low to medium grade metamorphism, altering their original mineralogy and textures. Studies of the chemical composition of the volcanic rocks in the greenstone belts show similarities to modern volcanic arc rocks, indicating a subduction-related origin for some of the volcanic sequences. The structural geology of the greenstone belts, including fold and fault patterns, supports the idea that they were influenced by tectonic processes similar to those in modern volcanic arcs. The greenstone belts here have a polyphase history, meaning they have been affected by multiple geological events over a long period, making their history more complex than a simple volcanic arc. So we have extremely ancient processes and erosion over billions of years to thank for the extreme riches that are being extracted from the Kalgoorlie area. Massive open pit mines exist, and there are many small scale prospectors that are also cashing in on the gold present all around the area. I hope you found this topic as interesting as I do, and as always, thanks for watching. The Gympie goldfields, located in southeast Queensland in Australia, are part of a broader geological structure known as the New England origin. The Gympie goldfields are the result of a series of geological processes that took place over hundreds of millions of years. From the initial deposition of marine sediments in a geosyncline to the complex tectonic interactions involving subduction, volcanic activity, and mountain building. Each step played a crucial role in concentrating gold into economically significant deposits. The hydrothermal systems, driven by the heat of rising magma, deposited gold in quartz veins, creating the rich mesothermal gold deposits that have made Gympie a notable gold mining region. Gympie is one of the closest goldfields to Brisbane. The Gympie goldfields were discovered in 1867. The amount of gold extracted from the Gympie goldfields is quite substantial. Over its mining history, the goldfield produced more than 3.5 million ounces of gold. The discovery of gold by James Nash in 1867 triggered a gold rush. The initial years saw a rapid influx of miners and the establishment of a thriving mining town. During this period, gold was primarily extracted from alluvial deposits, which is gold that is found in riverbeds and streams. Nash found gold in the alluvial deposits of the Mary River and its tributaries. While many nuggets were found in the Gympie goldfields, the exact record of the largest nuggets can be sparse due to the historical nature of the gold rush. However, some notable nuggets include the Curtis nugget, which is one of the most famous gold nuggets found in Gympie. This nugget weighed approximately 975 ounces, which is 27.7 kilograms, and it was discovered in 1868. It is one of the largest nuggets ever found in Queensland. Throughout the late 19th century, numerous other large nuggets were discovered in the region. Reports from the time mention several nuggets weighing over 100 ounces, which is 2.8 kilograms. Even today, gold prospectors in Gympie occasionally find gold nuggets using modern metal detectors. While the major gold rush days are over, the region's history and remaining gold deposits continue to attract hobbyists and small-scale miners. Alluvial gold is typically found as nuggets and flakes that have been eroded from the primary gold-bearing rock and transported by water. The ease of finding gold in riverbeds attracted thousands of prospectors to the area, leading to a gold rush. As the alluvial gold became scarcer, miners began to extract gold from deeper underground veins. The development of underground mining techniques allowed for the extraction of gold from quartz reefs. This period saw significant gold production, with numerous mines operating in the area. By the early 20th century, the easily accessible gold deposits were largely depleted, leading to a decline in mining activity. However, technological advancements and improved mining techniques allowed for intermittent mining activities throughout the 20th century. These activities focused on extracting gold from lower grade ores and remnants of older workings. In recent years, there has been renewed interest in the Gympie goldfields, with modern exploration and mining companies investigating the potential for new gold deposits. Advances in mining technology and exploration techniques have the potential to uncover additional resources in the region. But how did the goldfields here form? Well, this all somewhat started with the New England origin. I say somewhat for reasons that will become clear shortly. The New England origin was initially shaped by the deposition of thick marine sequences during the Devonian and Carboniferous periods, about 419 to 299 million years ago. These sequences were deposited in a geosyncline, a large-scale depression in the Earth's crust that collected sediments. The Gympie region's rocks tell a fascinating story of how the Earth's plates have moved and interacted over millions of years. Imagine the Earth's crust as a giant puzzle made of pieces called tectonic plates. Sometimes these plates collide. When an oceanic plate, which is denser and thinner, hits a continental plate, which is thicker and less dense, the oceanic plate gets pushed underneath in a process called subduction. As the oceanic plate moves under the continental plate, it scrapes off sediments, loose materials like sand, mud, and small rocks, and pieces of oceanic crust. These scraped off materials get piled and squeezed against the edge of the continental plate, forming a mix of rocks known as an accretionary wedge. The rocks in this accretionary wedge are not just piled up neatly, they are twisted, folded, and broken because of the immense pressure and movements during subduction. This makes them look very complex and jumbled, like a crumpled piece of paper. Some of these rocks are cleaved, which means they have split into thin layers due to intense pressure. Melange structures are areas where different types of rocks are mixed together chaotically, resembling a rocky stew. To put it simply, the Gympie region's geological formation can be visualised as a conveyor belt where the oceanic plate moves underneath the continental plate, scraping off loose material and rocks from the ocean floor. These materials get squished and piled up at the edge of the continental plate, much like how snow piles up in front of a snowplow. Due to the constant movement and immense pressure, these piled up materials get twisted and folded in many different ways. Imagine trying to push and squeeze a stack of papers. They wouldn't stay flat, but would crumple and fold. In this chaotic mix, you get a variety of rocks all jumbled together. Some rocks get split into layers, while others are mixed together like ingredients in a rocky salad. This process of subduction and the resulting formation of complex rock structures are crucial in understanding how gold deposits and other minerals come to be in regions like Gympie. The intense geological activity creates conditions that can concentrate valuable minerals, making them accessible for mining. Whilst associated with the New England origin, the Gympie province has its own designation. It has been interpreted as including components of an evolving volcanic arc that collided with the eastern margin of the Australian continent in the early to middle Triassic. This is why I said it's somewhat related to the New England origin, as the Gympie region actually developed outside of continental Australia, as a standalone volcanic arc in the open ocean. It was only during the Hunter-Bowen orogeny that it became accreted to mainland Australia. It's likely that the New England origin produced the magma needed to form the arc, but it was a separate entity that formed some distance away from Australia at its beginning stages. During the early to middle Paleozoic era, around 541 to 298 million years ago, Subduction of the Paleo-Pacific Oceanic Plate beneath the Australian continent led to the formation of volcanic arcs and the emplacement of granitic batholiths. This subduction was a key driver of the geological processes that formed the gold deposits in the region. The rising magmas carried gold and other minerals, which were deposited in the crust as the magmas cooled and crystallized. The Gympie region still exhibits geological features characteristic of ancient volcanic arc systems. The presence of volcanic rocks such as basalts and andesites indicates past volcanic activity associated with the volcanic arc. As the oceanic plate subducted beneath the continental plate, it generated significant heat and pressure. This caused partial melting of the subducted plate and the overlying mantle wedge, creating magma. The magma, being buoyant, rose through the Earth's crust, leading to volcanic activity at the surface. This volcanic activity formed a chain of volcanoes, similar to the modern-day Pacific Ring of Fire. The rising magma also intruded into the crust, forming large bodies of igneous rocks known as batholiths. These igneous intrusions played a crucial role in the mineralization processes that eventually led to the formation of gold deposits in the region. A major tectonic event, the Hunter-Bowen orogeny, occurred during the late Permian to early Triassic periods, about 260 to 250 million years ago. This event was characterized by intense folding, faulting, and metamorphism, significantly impacting the structure and mineralization of the Gympie goldfields, and it led to the accretion of it to mainland Australia. There are major faults in Gympie, which acted as conduits for gold-bearing fluids to rise and deposit auriferous quartz into the fractured Permian age sedimentary bedrock. The emplacement of granitic batholiths during the Siluro-Devonian period, approximately 425 to 400 million years ago, initiated hydrothermal systems. These systems involved the circulation of hot mineral-rich fluids through fractures and faults in the crust, leading to the deposition of gold in quartz veins and lodes. The hydrothermal fluids were primarily modified meteoric and magmatic fluids, which leached gold from the surrounding rocks and concentrated it into economically viable deposits. The Gympie goldfields are characterized by mesothermal quartz gold base metal sulfide deposits. These deposits formed at moderate temperatures of between 230 to 350 degrees Celsius and depths typically associated with mountain building events and hydrothermal fluid activity. The gold deposits in Gympie share similarities with other significant goldfields, such as Charter Towers and the Mother Lode deposits of California. To summarise, the formation of the Gympie goldfields involves subduction and subsequent accretion of oceanic materials onto the continental margin. Emplacement of granitic batholiths and associated volcanic activity provided heat and fluids for hydrothermal systems. The circulation of mineral-rich fluids through fractures and faults led to gold deposition in quartz veins. Multiple phases of tectonic activity, including the Hunter-Bowen orogeny, contributed to the structural deformation and mineralization of the region. As time goes on, I intend to cover many other goldfields across Australia and the world and explain the geological processes that led to their formation. I hope you found this as interesting as I do, and as always, thanks for watching. In Victoria, the most abundant gold-saturated rocks exist in the geological province known as the Castlemaine Group. This group of mudstones, sandstones, siltstones and shale was deposited by turbidites, which are underwater landslides some 485 to 470 million years ago. The Castlemaine Group is a host of sedimentary rocks that have been injected with gold-bearing quartz. From Bendigo to Ballarat, the richest goldfields are in areas where the Castlemaine Group has been exposed to the surface. They are represented by the blue colour on the geological map, and gold eroded en masse from this lithology. But the recent basaltic eruptions have covered much of it in parts of Western Victoria. But in this video we are heading far away from the Golden Triangle to an area southeast of Melbourne, and we are going to take a look at a geological anomaly that only exists in the Mornington Peninsula, at least in this part of Victoria, and I'll explain why gold exists in this region. The Mornington Peninsula is strange in that the typical strata that we find in Melbourne doesn't exist here. Instead, we have a small outcropping of the Castlemaine Group near Mount Martha. This is strange and rare. You will not find this outcropping anywhere else in Melbourne. Much of it has been covered by the preceding sedimentary deposits that make up the Melbourne region. This host of sedimentary rocks is appropriately named the Melbourne Formation, and it is joined by the Anderson Creek Formation, which in itself also hosts gold. This gold was mined in Warrandyte and in the Ringwood area, and these two sedimentary lithologies were deposited during the Silurian, which began 443.8 million years ago and ended 419.2 million years ago. But the Castlemaine group of rocks were deposited during the Ordovician, which is much older, with a date ranging from 485.4 million years ago to the start of the Silurian period 443.8 million years ago. The exposure of the Castlemaine group led to a gold rush that was short-lived but profitable for those who found and exploited the tiny land where the Castlemaine group existed on the Mornington Peninsula. There were 3 gold rushes in this area, but the 2 areas where gold was exploited and documented on geological maps are called the Bulldog Creek and Tubbarubba Creek gold diggings. These diggings commenced around 1851, and the workings consisted of both alluvial and hard rock mining. In 1895, a rich patch of gold was discovered near the old Tubbarubba diggings at Bulldog Creek. Volcanic eruptions occurred here during the Lutetian, some 47.8 to 41.2 million years ago, covering much of the Castlemaine group over with basaltic rocks. But you can still see small pockets where it is exposed. Along with this, we also have recently deposited sandstone known as the Red Bluff Sandstone, which also covers the Castlemaine group, and it was deposited between the Miocene to Pliocene, which spanned between 23 to 2.58 million years ago. Beneath the basalt and sandstone exists gold just waiting to be found, and the exposure of the Castlemaine group here proves this to be the case. The diggings were shallow and yielded some good gold for the prospectors who opened the field up. But today, the gold mining history of this area is largely forgotten about, sadly, which is why I wanted to make this video. Gold exists all throughout Melbourne. It's deep in most parts, but this shallow area where the Castlemaine group was exposed shows that Melbourne is hiding vast and valuable treasures beneath it. Like I've said previously, it's just hiding beneath cheeky basalt, and in this case also beneath cheeky sandstone. So grab a shovel and start digging. You never know what you'll find. These prospectors did, and they were greatly rewarded for their efforts. Thanks for watching. A few days ago, I got this comment on Queensland's Gympie Goldfields geology video that I made, to which I replied, challenge accepted. So it's time to follow through with that challenge. I love Western Australia. It's a beautiful place. The rocks are so ancient that it's awe-inspiring for me. It's probably my favourite place on Earth. The Pilbara craton formed as a result of successive geological processes of volcanism, sedimentation and tectonic activity that led to the accretion and stabilisation of ancient continental crust. Development of the craton involved several cycles of magmatism and metamorphism, which created its highly stable and ancient nature. The major rock type is Archean granite greenstone terrain, formed of ancient volcanic rocks known as greenstones and granitic intrusive rocks. Granite provided the craton with a stable, buoyant continental crust by solidifying as dense magma cooled below the Earth's surface during the Archean eon. Over time, repeated geological cycles of magmatism, tectonic activity, and metamorphism further consolidated these granitic formations and helped to create the craton's long-term stability and resistance to tectonic deformation. The Pilbara craton was the first mineralised craton, the first time that mineralisation was accreted into the Australian landmass. Gold in basin-hosted deposits was the very first mineral emplaced into the rocks of Pilbara. It is typically associated with the metamorphism of sedimentary basins, and the subsequent emplacement of mineralizing hydrothermal fluids that migrate through basins, precipitating gold and other metals in favourable structural and porous or permeable rock settings such as faults, fractures, and porous or permeable rocks. The northeastern part of the craton was deposited with gold, silver, copper, lead, and zinc between 3.5 and 3.47 billion years ago, and so the mineralisation of this great country commenced. Today, the Pilbara region continues to be explored for gold and other precious metals. Modern exploration techniques such as geophysical surveys and geochemical sampling help identify new targets for mining. The discovery of gold in conglomerates similar to those of the Witwatersrand Basin in South Africa has also generated significant interest in the region. The history of gold mining in the Pilbara region dates back to the late 19th century, when the first gold rushes occurred. Pioneers and prospectors flocked to the area, driven by the promise of rich gold deposits. The Marble Bar Gold Rush in the 1890s was one of the earliest and most significant gold rushes in the Pilbara region. This gold rush led to the establishment of a town and the development of numerous mines. The discovery of high-grade gold deposits attracted miners from all over Australia and beyond. The Nullagine Gold Rush was another major gold rush that occurred in the Nullagine area, where rich alluvial and lode gold deposits were found. This rush resulted in the development of several mining operations and contributed to the region's economic growth. In modern times, the Newman and Tom Price towns, which are primarily known for their iron ore mining, have also seen gold exploration and mining activities. Modern techniques and technologies have enabled the discovery and development of new gold deposits in these areas. The Karratha and Port Hedland coastal towns have become hubs for modern mining operations, with companies investing in exploration and development projects. The discovery of gold in conglomerates near Karratha has sparked renewed interest in the region. The Hemi gold discovery in 2020 was one of the most significant recent discoveries. Located in the Malina Basin near Port Hedland, this discovery has been hailed as a major breakthrough, highlighting the potential for large, high-grade gold deposits in the Pilbara region. The Pilbara region remains a key area for mineral exploration and mining. Shortly after the Pilbara craton began its life, the East Pilbara terrane formed between 3.525 to 3.165 billion years ago. And it is also around this time that the first volcanic and metamorphic gold, silver, and copper deposits were deposited in the Pilbara craton. Additional volcanic-derived molybdenum, silver, and copper was deposited 3.3 billion years ago, and additional copper and nickel was deposited 3.28 billion years ago. Between 3.26 and 3.24 billion years ago, additional basin-hosted deposits of gold, silver, copper, lead, and zinc were deposited, and another basin-hosted deposit of copper and zinc was deposited 3.12 billion years ago. The first deposits of iron were deposited 3.02 billion years ago, and similar to many of the previous deposits, this is another basin-hosted deposit. Iron can be deposited in basin-hosted deposits through a couple of ways. When iron-rich hydrothermal fluids or seawater discharge into the adjacent basin where anoxic conditions allow for both deep-sea hydrothermal deposits as well as iron seep deposits, where iron reacts with oxygen or other chemicals in the water to form iron minerals such as hematite or magnetite. These deposits tend to form in marine sedimentary basins, and alternate layers of iron-rich minerals and silica or other sediments settle down over time. However, back to the East Pilbara terrane. This terrane is one of the most important components of the Pilbara craton. It is formed by four major volcano-sedimentary groups and one formation. Basaltic volcanic rocks dominate the Warrawoona group, with less abundant felsic volcanic and sedimentary rocks. The Straley Pool Formation, with its characteristic carbonate siliclastic facies, and the earliest Archean stromatolite and microbial fossils, is one of the most well-known stratigraphic units in the Warrawoona group. Volcanics in the Kali group are a complex combination of mafic to ultramafic to felsic volcanic rocks, with interbedded siliclastic and chert, all of which suggest highly diverse volcanic activity. The rocks of the Sulphur Springs group are a mixed group of ultramafic, mafic, and felsic volcanic rocks and siliclastic sedimentary rocks, suggesting significant volcanic activity. The collection of clastic rocks, banded iron formations, basalt, and ultramafic and mafic seals in the Sonesville group reflects the wide range of depositional settings present during its formation. The greenstones of the East Pilbara terrane are fringed by granitic complexes of 5 supersuites. In geology, a supersuite is a large coherent assemblage of related rock suites that may have had a common origin or history within a significant time interval and geographical setting. That is, they may have been produced or affected by related tectonic or magmatic settings and have similar mineralogical, geochemical, and structural assemblages. The 5 supersuites are the Kalina, Tambina, Emu Pool, Cleland, and Mount Bilroth, which were concurrently formed with the felsic volcanic components of the greenstones, which formed by melting of a mafic parent rock, the heat and fluids from which were compatible for metamorphosis and mineralization of the adjacent rocks. The West Pilbara superterrane formed between 3.27 to 3.06 billion years ago. It consists of 3 granite greenstone terranes. Greenstone terranes are ancient geological formations composed primarily of metamorphosed volcanic and sedimentary rocks, typically greenish in colour due to the presence of minerals such as chlorite, actinolite, and epidote. These terranes are commonly found in Archean and Proterozoic cratons and are significant for their association with rich mineral deposits including gold and base metals. The three terrains are the Karratha terrain, which includes the Roburn group, composed of ultramafic, mafic and felsic volcanic rocks, intruded by the Karratha granodiorite and granites of the Maitland River and Orpheus supersuites. The shoal terrain comprises the Wando group, with mafic, ultramafic and felsic volcanic rocks and thin sedimentary units intruded by the Railway supersuite. The Regal terrain is a slab of basalt, peridotite and chert, possibly abducted from the ocean floor, overlying the Karratha terrain. Abduction is a geological process where oceanic crust is thrust over the edge of a continental plate, instead of being subducted beneath it, resulting in the emplacement of oceanic lithosphere onto continental crust. As a side note, if you're enjoying this video, please click the like button to help YouTube recommend it to others. Consider subscribing and clicking the bell icon to be notified of when we upload. We also have a Patreon if you'd like to support the channel, and you can find that both in the description and in a pinned comment down below. The Elizabeth Hill supersuite dates to around 3.07 billion years ago, and it intrudes both the East Pilbara terrain and West Pilbara superterrain, marking a significant geological event. Following this, we have the Kurana terrain, which formed between 3.20 to 2.89 billion years ago. Located in the southeastern part of the exposed craton, the Kurana terrain consists of two granitic supersuites and minor greenstone. This terrain highlights the complex interplay of volcanic and plutonic processes in the region's geological evolution. It was during this time period that more metamorphic derived gold deposits took place in the Pilbara craton, with an age of emplacement dating back to 2.96 billion years ago, followed by another basin-hosted deposit of copper, zinc, gold, lead, and silver at 2.95 billion years ago. Shortly after this, the first deposits of platinum occurred. Between 2.93 and 2.92 billion years ago, platinum, copper, nickel, gold, palladium, zinc, lead, titanium, rhodium, and the rare metal known as vanadium were deposited. Some derived from magmatic processes and others from basin-hosted deposits. The De Grey superbasin formed from 3.02 to 2.93 billion years ago. These basins are filled with sedimentary and volcanic rocks of the De Grey supergroup, which unconformably overlie the West Pilbara superterrain and East Pilbara terrain. After all this, the Pilbara craton's birth and evolution was solidified. Some additional volcanic deposits of cobalt, palladium, copper, and nickel took place 2.9 billion years ago, followed by volcanic deposits of gold, tantalum, and lithium. It is apparent that the gold-bearing rocks were at surface level around this point, as we have an erosional and supergene deposit of gold at 2.76 billion years ago. Supergene gold forms through the weathering and oxidation of primary gold deposits, where gold is dissolved and reprecipitated near the Earth's surface, often resulting in high purity secondary gold concentrations. This process typically enhances gold enrichment in the weathered zone, creating economically significant deposits. After this, the Yilgarn craton became highly active in regards to mineral deposits as its evolution continued, but that's the subject of another episode. One notable additional wave of metasomatic iron deposits occurred in Pilbara at 2.01 billion years ago. Regional metasomatic iron deposits are large-scale iron ore deposits formed through metasomatism, a process where existing rocks are chemically altered by the introduction of iron-rich fluids. These fluids percolate through the rock, replacing original minerals with iron-bearing minerals such as magnetite or hematite, often resulting in extensive and economically valuable iron ore deposits. After this, the Pilbara craton remained relatively silent until a new wave of volcanic-derived deposits of copper, silver, and gold occurred 650 million years ago. Advances in exploration technologies such as airborne geophysical surveys and remote sensing continue to uncover new targets for precious metal deposits. The ongoing research into the region's geological history and mineralization processes helps refine exploration strategies, making it possible to identify and develop new mining projects. While the Pilbara region offers significant opportunities for mineral exploration and mining, it also presents challenges. The remote and rugged terrain, coupled with extreme weather conditions, can make exploration and mining operations difficult. However, the region's rich mineral endowment and the potential for new discoveries make it an attractive destination for mining companies. As mining operations continue to expand in the Pilbara region, there is growing emphasis on sustainable and environmentally responsible practices. Mining companies are increasingly adopting measures to minimise environmental impact, manage water resources, and engage with local communities to ensure that mining activities contribute positively to the region's development. The geological evolution of the Pilbara region is a fascinating journey through billions of years of Earth's history. From the formation of the earliest crust to the deposition of precious metals and the development of modern mining operations, the Pilbara craton has played a significant role in shaping our understanding of geological processes and mineralization. The region's rich mineral endowment continues to attract exploration and mining activities, promising new discoveries and contributing to Western Australia's economic growth. As we look to the future, the Pilbara region remains a vital area for geological research, exploration, and sustainable mining practices. Thanks for watching. Are you interested in animals? I've just started the second channel called PaleoZoology that discusses extinct and extant animals with a current focus on the megafauna that once dominated and roamed Australia. I've released a video on the Marsupial Lion which existed in Australia during the time Indigenous Australians walked the continent. I've also covered the wombat that was the size of a car, known as the Diprotodon, or the largest terrestrial lizard known as the Megalania. I'd love to have you along for the journey as more videos are released. You can find a link to this channel and to the aforementioned videos in the description and in the pinned comment in the comment section. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.